Now let's notice another iteration of this type of an idea. Let's say that I have an A plus a B, and let's multiply that by A plus B. Let's FOIL that out. First times first produces an A squared. Outer terms produces an AB. Inner terms produces a BA or an AB. And last terms produces a B squared. Collector-like terms. So notice what happens here. I have a pattern that we can put up in our special box now. A plus B times A plus B will always produce an A squared plus 2 ABs plus a B squared. So another pattern or a special product that happens when we do that. So let's look at a couple examples here of seeing this played out. Let's look at x plus 3 squared. It's its binomial times itself. So that fits this pattern, a plus b times a plus b, doesn't it? Yeah, because it's x plus 3 times x plus 3. So this makes my first term squared, which is an x. So that produces an x squared, plus 2 times a and a b, which is a 2 times x times a 3, plus my last term squared, 3 times 3, which is a 9. Collect some terms here, or simplify, x squared, this plus a 6x, plus a 9. Now later we're going to assign this one even more of a unique name. This one's a perfect square trinomial, meaning that if I were to factor this down, or where did it come from? It came from an x plus 3 squared, a perfect binomial, or binomial, I square it, and it becomes a perfect square trinomial. Anyway, we'll say that for later, but if you hear that term, that's kind of where it originates from. Notice what I did not do here. If I had an x plus a 3 squared, notice that I did not make this an x squared plus a 3 squared. This 2 does not distribute over a summation. It only distributes over a product. X plus 3 squared does not equal x squared plus 3. And the reason why, if we FOILed it out like we saw over here, I have middle terms that I collect. And I have 2 sets of those middle terms, 2 sets of 3 x's. This process, those get lost. So be very, very careful not to create a shortcut where a shortcut does not exist. 3x plus 7 squared. I notice that fits one of these 3 special products, fits this last one, so I can use that formula. And again, it's not really a formula, it's just a pattern that we discovered over time. And when we discover a pattern over time, we can use that pattern to kind of help scoot us ahead a little bit quicker. So this becomes a squared, which is a 3x. So 3x squared plus 2 times a times b plus my b squared. Now let's just do our operations. 3x squared. You guys agree? 2 times 3x times a 7. 6 times 7, 42. X plus a 49. There you go. And this also might be a great time to kind of remember again what's happening here when we multiply an a plus b times an a plus b. So let's look at that geometrically or visually. Remember that we can write this as an a plus a b times an a plus a b. I'm going to divide this out. So this first part, this distance from here to here represents my A. This distance from here to here represents my B. The whole distance obviously represents the A plus the B. And likewise on the top. So what's the area of this first square? Well, it's a length A by A, so it makes an A squared. This one right here, it's a length of B times a height of A, which produces an AB. This rectangle down here, its dimensions are a and a b, which also produces an ab. And the dimensions of this last little box, it's a b by a b, which produces a b squared. So visually, you see that I have an a squared plus 2ab's plus this last little corner down here is a b squared. So geometrically, visually, my multiplication of binomials follows this pattern as well.